Hi there. In this video, we'll be talking about how to solve certain systems of equations algebraically. You've already used the calculator to visualize equations in terms of graphs and to find their intersections. And that visual approach is really helpful. But for certain cases, we can just solve it by hand, especially when we have linear equations. So we're talking about systems, which just means when we have more than one equation. And a solution would be a combination of variables that make all of the equations true. So we'll talk about two methods. I think it's good to be familiar with both methods because, in my opinion, sometimes one of them is easier than the other. But I won't force you to use one. If you really decide that you have a favorite method that you want to use over and over again, that's your decision. It might not be efficient, but you're allowed to do that. So one method is, if we want to solve a system, so here is our example, right? I want to know which combination of x and y make both of these true at the same time. We can do a substitution. So what we will do is we will try to figure out how to figure out what x or y is in terms of the other one in the easiest way possible. So what you might notice is that for this equation at the bottom, we just have y without a coefficient, which makes it easy to solve for. If I move the 2x to the other side, I have y equals 10 minus 2x. So then I can look at the other equation and rewrite this with a substitution. I know that 3x plus 4y is equal to 12. So I can rewrite that, but I know from the other equation that y is the same as 10 minus 2x. So I'm rewriting that equation now just with x. So we can solve this hopefully fairly easily. I'll distribute that 4. So we have negative 5x equals negative 28, and x is 28 over 5. Now we're not done. A solution here means figure out what is x and what is y. Once you know x, just find any equation, plug it in to solve for y. Probably the easiest one is here. So y would be 10 minus 2 times 28 fifths. And the fractions here are a little annoying, but we can do this. This would be 50 fifths minus 56 fifths, which is negative 6 fifths. So our solution here, this is one solution. What is x? What is y? Even though it's two numbers, that is a single solution. This is the combination of values where both of those equations are true at the same time. And whenever you have enough time, it's a good idea to check. The first equation says 3 times x plus 4 times y is supposed to be equal to 12. If I work through that, that's 84 over 5 minus 24 over 5, which is 60 over 5, which is 12. The second equation says 2x plus y. That's 56 over 5 minus 6 over 5, which is 50 over 5, which is 10. That also checks. So again, what I did is I looked at both of them. I noticed that right here I had y without a coefficient, which makes it really easy to isolate. I figured out what y is, and then I plugged into the other one. So try these, or try this one. So if you're doing this for the first time, hit pause, give it a shot. Okay, so for this one, I would notice that this x is all by itself in the first equation. So I could rewrite this first equation to say that x is 5 minus 3y. So then I could substitute here, x is 5 minus 3y. And I'll solve this for y. Distribute means negative 10 plus 6y minus 4y is equal to negative 5. So negative 10 plus 2y is equal to negative 5. 2y is equal to 10. And 2y is equal to 5. Whoops. And y is 5 halves. If I substitute back, x is 5 minus 3y. So that's 10 halves minus 15 halves, which is negative 5 halves. So my solution, I'll put it over here, is x equals negative 5 halves, y equals 5 halves. And if we wanted to check that, negative 5 halves plus 3 copies of 5 halves is 10 halves, which is 5. That works. Negative 2 copies of x minus 4 copies of y. That's 5 minus 10, which is negative 5, and that checks. I might not do all the checking as I go through this, but it is a good habit. So these are substitution ways. We figure out what either x or y is, and we plug that into the other one. Another method is called elimination. Elimination is when we add up entire equations to get a new equation in the hope that the new equation is simpler than something we had before. So here's an example. I have that 4x plus 2y is equal to 9, but also that negative 4x plus 3y is equal to 16. So what that means is if I add together all of the things on the left, that should be the same as adding together all of the things on the right. If left is equal to left and left is equal to left, then the total of everything on the left should be the same as the total of everything on the right. If I do that, what I notice is that the 4x here and the negative 4x here basically cancel each other out. That's why we call this elimination. So when we add all this up, this part's basically just 0, and we're left with 5 copies of y. The x's cancel out. And on the right-hand side, we get 25, so that means y is equal to 5. Once I know y is equal to 5, I can substitute that into either equation. I'll pick the one without the negatives. So 4x plus 2y, which I now know is 2 times 5 or 10, equals 9. So 4x equals negative 1, and x equals negative 1/4. So our solution here is x equals negative 1/4, and y equals 5. Here's another one. Now here, if we add things up right away, nothing's going to cancel. So what we might want to do is we might want to say, could I multiply in a clever way to create things that cancel? And try looking at some of your smaller coefficients. So I might notice I have 2s here and 3s here. I could turn those both into 6. So what I could do is I could take my top equation and multiply the entire thing by the number 3. That would give me 6s plus 21t is equal to 12. And I want to cancel that 6x with a negative 6s. I could get a negative 6s if I multiply the entire second equation by negative 2. Negative 6s minus 10t equals 10. Right, this is a little more challenging, but we can still create that elimination if we manipulate these equations. So we'll add everything up. The s's cancel. With the t's, 21t minus 10t gives us 11t left and 22 over here. So t is equal to 2. And then we can just substitute that in. So from here, 2s plus 7 times t is now 14 equals 4. So 2s equals negative 10, s equals negative 5. And our solution is s equals negative 5, t equals 2. And I am just quickly checking in my head that that looks correct. Yes. So here are a couple more for you to check, right? For you to try and check. Again, if you're doing this for the first time, pause and really try this on your own. Okay, so my solutions. Here I notice that the 8y and the negative 8y will cancel right away. So when I add this up, I get 3x equals 12, which means x equals 4. If I plug that in to, say, the first equation, I have negative 8 plus 8y equals negative 8. So 8y equals 0 and y equals 0. That's not an error. Sometimes when we solve things, the solution is the number 0. So our solution here would be the combination x equals 4 and y equals 0. For this one, I want to create cancellation. I could look at 7 and 2 and say I could turn both of those into 14. So maybe I'll multiply the top by 2, and I get 6a plus 14b equals 30. And then I'll multiply the bottom one by negative 7. I would have negative 35a minus 14b equals 28. So when I add that up, I would have negative 29a, the b's cancel, equals 58. And this actually turns out pretty nice. We'll just get a equals negative 2. So if a equals negative 2, I can plug in here. So 3 times negative 2 is negative 6, plus 7b is equal to 15, which means 7b is equal to 21, and b is equal to 3, and this is our solution. Sometimes the numbers are a little bit annoying. Often, not always, but often someone will have worked this out so that you actually get pretty nice numbers, even if it looks awkward. Now, not every system has a solution, and not every system has a unique solution. So if you try the elimination method and you find that everything cancels away, that means something a little unusual is going on. So let's look at this example. I could create cancellation, create elimination, by leaving the second equation the same and multiplying the first equation by 2. But then I notice the x's get eliminated and the y's get eliminated, and I'm left with 0 on the left and negative 4 on the right. This is impossible, right? We know that 0 and negative 4 are different numbers. What's happening here is it's saying the only way for this to be possible is if 0 is equal to negative 4, which clearly is impossible. So this has no solution. This is sometimes called an inconsistent system. And it is literally impossible for both equations to be true at the same time. If you try to solve this one by graphing, you would get 2 lines that never intersect. They're parallel. So there is no solution. No matter how hard you try, you will never find a combination of x and y that make both of these equations true at the same time. Now for this one, I'm going to multiply the top equation by negative 3. And I would have negative 12x minus 3y equals negative 18. 12x plus 3y equals 18. And when I add this up, I get 0 equals 0, which is certainly true, but it doesn't really tell me anything about x and y. So this is our signal that maybe x or y do not have to be specific values, that we have some flexibility. And if you notice, the second equation is really just triple the first equation. The second equation doesn't give us any new information. If I already know that 4x plus y is equal to 6, then I could have deduced that 12x plus 3y is equal to 18. So we don't really have 2 pieces of information here, we just have 1. If you graphed this, you'd draw the same line twice. So it turns out any combination of x and y on the graph of 4x plus y equals 6, in slope-intercept form, that's y equals negative 4x plus 6, will be a solution. So there are, in fact, lots and lots and lots of solutions. I could have x equals 1 and y equals 2. I could have x equals 5 and y equals, doing this in my head, negative 14. I could have x equals negative 1 and y equals 10, etc. Lots and lots of combinations of x and y would make this work. So if this were a test or quiz problem, I might just say, if there's more than one solution, say so. So here we could just say there are multiple solutions, in fact, infinitely many. If you have a linear system like this, if it has more than one solution, it in fact has infinitely many. Okay, that is the end of this section.